Good morning. Welcome, everyone. I'm really happy this morning. I'm here with Stephen, who's in New Zealand. Thank you so much, Stephen, for doing this webinar in New Zealand for us. It's really appreciated. So this is super exciting. This is part 2 to the basic event sourcing design principles with unique constraints as an example. And if you'd like to ask questions, please ask them at the end and Stephen will answer them then. But take it away, Stephen.
Okay, thanks, Tasha. So in the last webinar, we introduced the aggregate and process manager patterns and talked about how it respectfully enables transactional and eventual consistency. In this second part of the webinar, we're going to dig deeper into aggregates and process managers and see how we can implement one in Event Store DB while we review some of the concepts that we learned in part 1. So without further ado, let's get right into it. So it's common for your application to have some business rules that are enforced on a set of data objects or entities. So when you change the application, you expect the change to satisfy these rules. And this is important because it ensures your data is valid, so it can be trusted across organization. However, when data is changed and stored in an inconsistent state, this can cause major confusion in your business operation, wasting precious time to correct and can be costly to fix. In the software application development, enforcing rules across multiple objects is not always easy because of 2 big reasons. First, there can be multiple users trying to update these objects at the same time, which means their updates can overwrite each other, causing inconsistency. Secondly, there can be multiple entry points to update these objects, which means you have to spend more effort to ensure they all enforce the rule consistently. Otherwise, the rule can be violated. For example, say you have a website that has some kind of user registration mechanism. To register, the user has to provide a username, email, and password. When your application receives a registration request, it creates a user object and inserts it into the database. And over time, say a few of these objects are created. However, there's a rule that must be enforced before a user can register. The rule is that the username must be unique and cannot clash with the names of other registered users. This ensures it can be used for, say, logging into your application. Naively, you can achieve this with a simple piece of logic that checks the uniqueness of the username before registration. For example, suppose Dan wants to register and sends a request to the application. It then selects all the records from the user table to check if the username Dan already exists. If not, then it inserts Dan into the table. So while this approach is straightforward, it has a few problems which can cause the uniqueness rule to be violated. Firstly, there can be multiple users who try to register with the same name at the same time. With race condition, you may have 2 different Dans who are trying to register. Both makes the request and calls the same registration application at the same time. It would then retrieve the same list of users from the database and will both verify that Dan is not on the list. As a result, both calls will insert a Dan into the database, resulting 2 copies of the same user, which breaks the uniqueness rule. This problem often happens when logs and transactions are not in place to protect the integrity of the user data. This is an example of a race condition, and it's the first reason why maintaining data consistency across multiple objects is challenging. The second reason why maintaining consistency across multiple objects is hard is because application can easily have multiple entry points to the user table where the rule is not enforced. This can be very common, especially in legacy applications, to contain different ways to update the same table. For example, other than the common user registration function, there can be another piece of logic that allows administrator to register a new user, say through a stored procedure. Maybe there's a rewrite of the registration logic, but the old and the new versions are used in different areas of the application. And sometimes business users even directly register user by updating the table without any database security measures in place. But whether it's all these things are due to communication issue, design oversight, the uniqueness rules are not enforced in these alternative entry points, and it introduces risk of data inconsistency. So in this example, Dan has already been registered and is in the database, but there are two other users who still want to register as Dan. They would do so over two separate logic. The first piece of logic is designed to check the uniqueness and rejects Dan's request to register again. The second piece of logic does not have the same check in place. This is going to insert an extra Dan in the database, resulting two copies of it, which breaks the uniqueness rule. This problem often happens when pieces of logic that share data are not centralized in one place. So again, the two reasons why it's not easy to enforce rules across objects is one, multiple users can get into race condition causing update issues, and two, multiple entry points make it hard to enforce rule when there isn't centralized checking logic for it. So the aggregate pattern is designed to help you solve these problems by enforcing business rules across multiple objects and keep your data consistent. So you were introduced this pattern in the previous webinar, but let's have a quick review of it right now. So the pattern is pretty simple. So in short, the aggregate is a set of objects that must be changed together, usually over a transaction. For example, here you have an aggregate that represents all the users in the application. The aggregate right now consists of the user objects for Ada, Bob, and Kat. The aggregate always have a root object that has a reference to all the objects in the aggregate. This object is called the aggregate root. In this case, we're going to name it the user's aggregate root. It's solely responsible for all changes to the aggregate and forces any rules across the objects in the aggregate. So for example, the user aggregate root object has an array of users that holds references to all the users. And a register method is the single point of entry to any new user registration. The register method is responsible to enforce the username uniqueness rule. Next, the aggregate makes sure no objects outside it can access it unless it's done through the root. If an external object wants to update the aggregate, it can be done through the user aggregate root. However, any object that wants to update it through, like say, a backdoor behind the root will not be possible. You can enforce this by object encapsulation and private public access modifiers to limit access to the internal objects. For example, the user list can be made private so that no object outside it can access or modify it. On the other hand, the register method on the aggregate root is public because we want outside objects to access the aggregate through the root only. Lastly, any change to the aggregate, whether it's one or many within the aggregate, has to be saved to the database together within a single transaction. This protects the object so that the race condition cannot break business rules. We say that these objects are within a consistency boundary such that any change has to be saved transactionally and atomically together. So with all these properties, the aggregate establishes a transactionally consistent boundary around its object, which makes it easy to ensure business rules across the objects. So let's zoom out a bit and see how the aggregate pattern fits in a typical application and the process of how it is used. The flow starts with the user, say Dan again, submitting a registration to an application. This is usually a web controller or request handler that receives the registration. Next, the handler loads the aggregate from the database into the memory, retrieving all the objects within the aggregate. In this case, this is probably like a select star from user table, which retrieves all the user objects, including Ada, Bob, and Cat. The handler then calls the register method of the aggregate and passes Dan's information into it. And since Dan's username is not found here, the aggregate considers the change valid, and a new user object for Dan is added to the aggregate. Finally, the handler is then responsible to save the changes to the aggregate back to the database. In this case, probably a simple insert to add Dan's record into a user table. Note that handlers should perform all these actions from loading and saving the aggregate inside a transaction to avoid race condition. So in the next section, we're going to see how we can implement an event source aggregate with Event Store DB. And we will walk through some samples on how we do this. But before we start, I just want to make sure, to make a disclaimer that the code that are presented here are largely going to be pseudocode that is based on C#. So, and also there might be syntax errors and code that's not optimized, but bear with me because we did this so that we can maximize the learning experience for everybody. So let's start off with a very simple example. So here we have a user's aggregate root that represents the gatekeeper for any changes against any user. Notice how it has references to all users in the application, but it is set to private so that no other external objects can access it. At the bottom, you can also see the class definition of the user object. For now, it's just simple with the name, email, and password. It also has a register method that handles user registration that accepts the new user's information. It is the method's job to enforce the uniqueness rule so that the usernames are not duplicated. And if the rule is satisfied, the registration is applied to the aggregate to represent a change. So let's implement this method. First of all, to enforce the uniqueness rule, you can find all users in the list that matches the registration's user. In C#, this can be done with the where method, which in this case loops through all the users in the list and looks for a registered user with the same name. If an existing user is found, then you can reject the registration by throwing an exception. The validation code to enforce a business rule in an aggregate can be just as simple as this. Next step, we need to apply the change to the aggregate after it passes the rule check. In this case, you can create a new user object to represent the newly registered user and add it to the list of users in the aggregate. With this added, any subsequent registration with the same username will be rejected. Finally, to make this aggregate compatible with event sourcing, you will have to track this change with an event. In event sourcing, an event represents a change in the application. To track all the changes to the aggregate, you need to introduce a change list that stores all the changes or events created. Events in this list will be extracted and saved to the event store after all the changes are made. Next up, you need to introduce an event that represents this user registration. You can create a new event called user registered event with a few simple properties like username, email, and password. And with this, in your register method, you can create this new event after the business rule check and add it to the change list. This completes the first draft of the aggregate root, which is now able to register a new user. To summarize this, you will see how the event source aggregate handles a request for change and how it enforces the rules amongst the objects in the aggregate and how it stores changes made into the change list. Next, you're going to see how you can load this aggregate root from the event store so that you can prepare change for it. To load an event sourced aggregate, you need a list of events from event store DB that represents all the changes made to the user's aggregate. This list of events usually come from what we call an event stream, and you will explore this more later in this webinar. There are many ways you can load an aggregate, but for simplicity, you see how it's loaded through the constructor. The constructor here takes a list of events, and its goal is to construct the aggregate by replaying its events to rebuild its state. In this case, the only state in the aggregate is just the user's list. The constructor will replay the events one by one from the oldest to the latest and rebuild the user's list one event at a time as if it is happening right now. For example, when you replay and find a user registered event, you can apply the event to the aggregate in the same way we did when the action was first taken. In this case, we'd create a new user and add the user to the list. If you compare this with the register method from before, you notice that this snippet is exactly the same as the one in the constructor. And by design, it should, because we're trying to rebuild the aggregate in the same way as it happened before. In fact, most of the time we will extract this snippet out into its own separate method so that both the constructor and the action will share the same logic. This method is often called the apply method, where we apply the event to the objects in the aggregate. And this is how simple aggregate can be implemented. So now that you've learned how to implement an event-sourced aggregate, let's take a look at how we can save and load it from an event store like Event Store DB. So Event Store DB is a database designed from scratch for event sourcing, and it has many features that will be naturally useful for you to build event source applications. So out of the many features, there are three important ones that an event store must have to support event sourcing. Firstly, it must be able to save or append events into a sequence log. It needs to be sequenced because the order of events matter when they are replayed. Secondly, it must be able to load or read events from the sequence log in the same order that they are saved. Finally, while an event is being appended, there must be some locking or transaction mechanism on the sequence log to prevent race conditions that you've learned just now. In Event Store DB, this sequence log is called an event stream. Event Store DB is made up of many streams where events can be appended to. And each stream is independent from each other and contains their own events, much like how a table contains its own records that are independent from other tables. In Event Store DB, an aggregate is represented by its own dedicated stream for its events. So for example, for the user's aggregate, there should be a user stream. If there is, say, a products aggregate that contains the product catalog for your business, there should be a product stream. And if there is an aggregate for each order for your business, there would be a stream for each order, which is usually named For example, order 1, 2, order 3, and so on and so on. To append events into a stream, you will typically call the append function on the event store DB client with the stream's name and a list of events for append. For now, just ignore the stream state.any there since that is related to locking, and we'll have more on that later. Read operations on event store DB are usually done on stream in a direction going forward, beginning from the start of the stream. So now that you know how streams work in Event Store DB, let's see how we can integrate it with an event-sourced aggregate. So before we start, let's see how you can create a database connection to Event Store DB. It is actually quite simple, and you can provide a connection string like this one here and use it to create an event store client. But don't worry about how to construct a connection string right now. You can check out the Event Store DB documentations on the developer's site for more information on this. But as I mentioned before, the aggregate is usually loaded from a piece of application logic, like a web request handler. So let's say you have a HTTP post action at the user's register endpoint. The endpoint accepts a JSON body with the parameters username, email, and password. The handler will execute a few things. First, it will load the aggregate from the stream, then executes the action with the aggregate, and saves the aggregate back to the stream. And finally, this has to be completed within a transaction. Loading the aggregate for the first step is pretty simple. You first read all the events from the user's aggregate stream, and then pass the events to the constructor that we just created a while ago, which will give you a new instance of the aggregate. In the second step, you just have to simply take the aggregate and call its register function. Remember, we implemented this just a while ago, and it will register the user and generate an event for it. In the third step, you will extract the new event from the user's aggregate by calling the changes property, and then append them to the user stream in Event Store DB. In short, this is how you load and save an event from an event source aggregate to make a change to it. In the final step, we will have to complete all these operations in one transaction so that it can be protected from race conditions. So let's consider we have two competing users trying to register the same username at the same time. In Event Store DB, a sequence number is provided for each appended event, which can track the version number of the stream. Here, for example, the user stream version is at number 1, meaning that this is the first revision of the aggregate. To begin, both of them reads the stream and sees that it contains two users, Ada and Bob. They both also make note of the current version number of the stream, which is version 1. Next, both of them try to register cat to the application. And when they do that, they'll also have to mention which version of the stream they last read, which is also version 1. Let's say the first user won and the race won the race and was able to register first. The user list is updated with cat successfully. Notice that at the same time, the version is incremented from 1 to 2. And immediately following this, the second user wants to register cat as well to the application. However, The database with optimistic lock will reject this update because the request expected version is 1. Because the request expected version 1 in the database, but the database is already at version 2. If it is not for this, there will be 2 copies of cat in the database, breaking the uniqueness rule. And this way, you will be able to avoid problems like these that are caused by race conditions when you use optimistic locking in Event Store DB. So now that you understand how optimistic locking works in Event Store DB, let's see how we can implement this in our code. So here you're back in the user registration handler where it's loading and saving the aggregate. To add optimistic locking to this, let's make a few small updates. There are 5 steps to update an aggregate with optimistic locking. First, you need to read the stream that you want to update. Second, take a look at the events in the stream and make note of the event number of the last event. Third, perform the aggregate action by calling the register function, and this generates a new event. And fourth, append this new event from the aggregate along with the last event number you made note just now. This will tell the append that you're expecting the stream that has not been updated since you last read it. Finally, if you won the race and no one else updated the stream before you, then the append will succeed. Otherwise, an error will be raised, meaning it is blocked by the optimistic lock. In this case, you will have to retry the registration process and just hope that no one else is doing it at the same time again. So while the aggregate is an awesome pattern to protect data consistency, it has some drawbacks when it's put into the extreme. For example, remember the goal of the user registration aggregate is to enforce the username uniqueness rule so that we don't allow someone else to register with a username that already exists. To achieve this, we usually stuff all the user objects inside this aggregate so that it can act like a turnstile or a gatekeeper whose job is to only accept registrations that don't break the rule. This means every time we register, the aggregate will be locked so that the other users cannot register at the same time. And as you remember just a moment ago, registrations that are blocked by the lock will have to retry the process again and again, costing the user some extra time when it happens. In all fairness, if there isn't a lot of people using the application, then this doesn't really matter. Say if on a daily basis, there's only an average of 1 user registered per day. The chance that 2 users are going to register at the same split second is very, 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 very slim. However, let's look at this from another extreme. Say your marketing department spent millions of dollars on an extremely successful Super Bowl advertising campaign, and out of nowhere, millions of users want to register. Within a short period of time, you could be receiving tens of thousands of requests per second. And say it takes around a millisecond to process each request, and there are millions of requests. What are the chances that 2 users are going to register at the same time? And with the users retrying due to a locked up aggregate, how long would it take for an average user to register? It can take a while for sure. You can see that an aggregate that locks up all the users don't necessarily make much sense in this scenario. And this is a once in a lifetime opportunity that can be in jeopardy. It's the job for the aggregate to enforce the business rule, but in this case, is missing out on millions of dollars of revenue and new users justified? This is the problem when we have an overly large cluster aggregate. One alternative that we mentioned in the last webinar is to break this aggregate down into smaller ones instead. And to do this, instead of one large one that stores a reference to all users, we have one aggregate per users that have no reference with each other. So what happens now when you have tens and thousands of registration per second? Well, instead of the large aggregate locking everything up, registrations can be completed much faster than before. This is because there's no locking across users anymore, and so the application can process registrations without being blocked by other users in this endless retry loop. So this is good news, right? Or is it? What about the uniqueness rule? Were we able to make sure we don't have users with duplicate names? Surely, perhaps we can read all the user stream at once and check whether the new username is unique or not before we register it. However, this can cause problems because by the time we complete reading all the users, another user with the same name could have registered it first, which then breaks the rule. Again, this happens because of race condition and the fact that there's no transaction to protect the data from it. Well, then you may say, okay, perhaps let's introduce a transaction across the user aggregates so that each time a user is registered, we can protect it from race condition. But now, if we added a transaction across all of them, isn't this just equivalent to the large cluster aggregate that we had just now, which has the same locking problem that we saw? So, is there a way to enforce the constraints while registrations are not being locked up? Yes, there is. And we can use the process manager for this. This process manager pattern is actually quite simple. Think of it as an object that monitors a group of aggregates and is responsible to align them to a business rule. If one of the aggregates make a change that breaks the business rule, the process manager can detect it and coordinate a change amongst the aggregate to fix it. For example, we can have a process manager that listens to user registered events across all the user aggregates in our previous example. Its job is to make sure user's name will be unique. Internally, it can keep a list of unique user names, and each time it receives a registered event, it will check if its username is already in the list, and if not, then it will add the new name to the list. So, for example, say Ada have just registered with the application, and its aggregate generates and publishes a user registered event. Since the process manager is subscribed and listening to all the user registered events, it picks up Ada's registration and adds her name to the user list. Subsequently, say Bob, Kat, and Dan also registered, and their events are picked up by the process manager, and it's also added to the list. So far, all the names are unique. A few days later, there was another user who also registered with the same name, Dan. And since we don't perform uniqueness check at registration time anymore, this user was registered successfully. At this moment, the uniqueness rule has been violated with two Dans in the application at the same time. The process manager receives the event for this registration, and since Dan is already on the list, it detects that the rule has been violated. There are many ways to handle this problem, but for some simplicity, let's say the process manager just deactivates this user right away. And when it is deactivated, then there's only one then in the application, and the uniqueness rule is satisfied once again. This is an example of how a process manager can enforce some business rule and do it without using any transactions. So how does this compare to the large aggregate approach? We can see that with the process manager approach, the uniqueness rule can be temporarily broken at a particular moment. And once the process manager detects this, it will fix it as soon as it can. And since the process manager approach uses many small user aggregates, there are no logs between them and scales better when you need to handle huge loads of requests. Each individual registration and other operations can be completed without blocking each other. This is different compared to the large aggregate approach where the uniqueness rule is strictly enforced using transactions, and so the rule cannot be violated at any time. On the other hand, since all the users are locked up in the large aggregate approach, this becomes somewhat infeasible when the aggregate has to handle very, very large numbers of requests in a short period of time. So, which way is better when it comes to modeling your stream and aggregates? There's no one best way to design your streams, and the choice between a process manager and a cluster of aggregates always come down to scalability versus consistency. If your operation needs to handle a huge number of changes, and it doesn't matter if consistency is compromised temporarily, then a process manager approach can help. However, if your operation requires your data to be always consistent and you are not dealing with large numbers of changes, then the large aggregate approach might be better. Also note that these two approaches can also be mixed so that you can have different sizes of aggregates that logs across different objects. And in the meantime, you can also have process managers that can handle and fix problems between these aggregates. The different techniques of how we do this and the trade-offs and the strategies they present will be something that we take a look in the next webinar. So in this final section, let's take a look at how a process manager can be implemented with event sourcing using Event Store DB. Process managers that use Event Store DB are typically hosted in its own application that listens for events that are generated. In these type of events, events from Event Store DB can be subscribed by using Event Store DB's subscription mechanism. The simplest way to subscribe to Event Store DB is to subscribe to all its events with the client using what we call the catch-up subscription. In this case, I'm subscribing to all events in the database. This will return a collection of events that you can for loop against, and it returns events from the very first one to the most recent one. The catch-up subscription is special in the sense that once all the events are caught up and handled, it will automatically go into listening mode, or what we call the live mode. And in this mode, the for loop is blocked as it listens to new events from the database. And when new events are appended and published, and it gets received by this, then it will enter the loop. So for example, if there are 3 events in the database right now, the loop here will be executed 3 times first, and then it's going to block itself. And when a new event is received, it will unblock itself and enter the loop once again, and block again until another event is received. While subscribing to every event in the database is a good start here, we only need a small subset of events. So to filter out the events that we don't need, we can use the server-side filter. In this case, we use a regular expression filter to make the subscription only listen to user-registered events. And now that we've set up the subscription, let's see how we use it to fix the duplication issue. Here, First, we introduce a user list that we'll use to capture only unique usernames found from the events. When we handle a registered event, we first check if the username is in the event, that's in the event is found in the list. And if it's not, then we're going to add it to the list. However, if it is already in the list, then we can call a function from, say, an API layer that will deactivate the user. This way, the user with the duplicated name is not active anymore, and the uniqueness rule is satisfied. While this is a really simple process manager that shows how to enforce business rules, there is a flaw in this design. If the process manager crashes midway, it has no way to recover what it has achieved so far. So, for example, if we have processed 10,000 registered events and it crashes, then there's no good way to know where the process manager was at just before the crash. You would typically have to restart the process manager again, which would then have to reprocess the 10,000 events again. This can be a problem in a few ways because, one, it may take a while to reprocess these events again, and two, depending on how the code is implemented, you may not want to reprocess the events the same way again. This is especially the case when processing involves, say, emailing the customer. And if you have to repeatedly email the customer each time you restart the process manager, then they may complain about the spam. So to tackle this, you can save a checkpoint after you process an event so that you can store the progress along the way. In Event Store DB, every event has what we call a position on the global event log, which is called the all log. It is a number that represents where the event is on the log, which is always going to be ordered by append time. This position can be used as a checkpoint, and the checkpoint can be saved in any type of persistent storage on disk, and it's common to save this on, say, Event Store DB or a separate relational database. So here we have the process manager code again, and we want to save a checkpoint whenever we process an event from the subscription. To do this, we can create an event. I'm going to call it a username checkpoint added. We will then add the event's position to it. Remember that in Event Store DB, the position is the number that represents where the event is on the all log. Next step, we can append this checkpoint event to a new username checkpoint stream that is only used to save the checkpoint for this process manager. So now that we know how to save a checkpoint, let's take a look at how we can load the checkpoint so that the process manager state can be recovered if it crashes. So to retrieve the checkpoint, we first read the username checkpoint stream where all the checkpoints are stored. And since the latest checkpoint is always going to be at the end of the stream, we will read the stream backwards from the end, and we will only read a maximum of one event. Next, we will define a variable for the checkpoint and first check whether or not the checkpoint stream can be found in the first place. If it's found, then we're going to set the variable to the checkpoint. Otherwise, it's going to just stay as null. Now that we have the checkpoint, we want to load the process manager state up to this position. And to do this, we will replay all the events from the beginning of time up to the checkpoint as if it's processing the events. First of all, we'll check whether there is a checkpoint or not at the moment. And if there isn't one, there's no point in loading anything anyway. Next, we'll read the events from the all log. And this is similar to how we subscribe all the events from it. And we can then replay these events in order so that we can rebuild the state of the process manager. We do this by repeating the same operation as we did while we were processing the events before. We check whether we can find the username in the user list, and if not, then we're going to add to it. However, if it already exists, then we don't want to repeat and deactivate the user again. Remember, our goal here is to load the process manager state and not repeat actions that has been taken. The process manager state for us is the list of unique usernames, and as long as we can rebuild this list, we don't have to repeat other actions. This is especially if actions like deactivating user and emailing can cause unintended side effects. So right now, this will replay all the events from the database from the beginning of time to now, which is not exactly what we want. Since we're only loading up the state to the checkpoint, we only want to replay events up to this position. To do this, we simply check the position of the event we just replayed and break out of the for loop if we already have reached the checkpoint. After this step, we have successfully loaded the state of the process manager. The last thing we need to do is to integrate this with the subscription logic we worked on just now. This way, we can subscribe and listen to all the events that are coming after the checkpoint. Here, we have added the subscription code that we worked on before this. And finally, we have built a simple process manager with checkpoint. To summarize, there are 5 steps in this process. First, we read the checkpoint from our persistent storage. Second, we load the process manager to the latest state by replaying all the events and rebuilding the unique user list up to the checkpoint. Next, we subscribe to all the events from the position of the checkpoint. And then we handle we handle and process each event that is received from the subscription. And for each event that we handled, we will save the checkpoint so that we can recover from it if the process manager crashes midway. So let's summarize what you have learned in this webinar. So firstly, you took a look at how the aggregate pattern can be used to enforce uniqueness constraint. You then found out how to implement an event source aggregate using event store DB. Next, you explored the drawbacks of aggregate, especially when scalability is needed. You then checked out the process manager pattern and how it can provide scalability when temporary data inconsistency is okay. And then finally, you learned how to implement a process manager with checkpoint using event store DB. In the next part of the series, we're going to take a closer look at how to balance aggregate and process manager for unique constraints. We're going to check out the different strategies we can use and then the trade-offs between these strategies and when we can use it. So with this, I want to say big thanks and hope you've enjoyed this webinar.
Thank you so much, Stephen. That was awesome. If you'd like to ask any questions, please do so now. We can see them in the chat. We do actually have a few already, which is lovely. So does optimistic lock rejection happen only if the client tries to save data that breaks the uniqueness?
No, it doesn't. So, I mean, the uniqueness, breaking the uniqueness was just an example of what I was trying to protect there with optimistic lock. But Certainly, optimistic lock can be used to reject anytime when you have two users trying to save something to the same stream at the same time. So again, we're trying to prevent some kind of update issues with race conditions. So that is the key point, and not so much the uniqueness rule.
Okay, and the next one is, in what version of ESDB catch-up subscriptions was introduced?
That's a very good question, and I think it's definitely before my time that I got to Event Store DB. When I first used Event Store DB, it was version 5, and it had catch-up subscription already. I suspect it's been there for a very, very long time. So sorry, I don't know the exact version, but I'm guessing it would be something like version 3 or 4.
How would you handle the process time between the deactivated user and recording the checkpoint, meaning it will retry that same action that actually already happened? Maybe an email?
Let me try to reread this a bit. So how would you handle the process dying between deactivate user? Yes, that's a great point. You caught that. So in that case, right? Yeah, in this case, what you have to do is in the aggregate itself, you have to be able to manage idempotent deactivation. This is really what it is, because certainly, when it died during that particular moment, then it's not saved in the checkpoint, and so of course, you have to replay that again. So unfortunately, there's nothing much you really can do there. It's just like most a lot of distributed kind of operations. It's it's hard to get a exact one's processing, and so in this case, in this particular case, it will have to be at least once processing, which means that it has to be run multiple times.
Wonderful. Well, if you have any more questions, please let either Stephen or I know, and we will get back to you. Looking forward to part 3, Stephen, and we shall be launching that very soon. Thank you so much for joining us, everyone.